You might have been wondering why we skipped the first few chapters. Were you like, well, Linda, why are you going out of order? And the biggest reason that I do that is that the thing people struggle with the most is which piece of projectile motion is changing. And with forces, what I want to emphasize to you, because I did it over the last few videos, I said that I have to have, I can't sing, I'm sorry about that. I have to have a net force to change a velocity. In other words, I have to have a net force to accelerate, to change velocity. This thing here is like the most important piece of everything you're going to do. Because what boggles people's minds is that velocity, the way we treat things mathematically, is not just something that we make up for funsies. It is legit. So these things are component behavior. So remember, we were breaking our forces down into components, into X and Y components, looking at the forces acting in those different directions. So that wasn't just for nothing or just an exercise in making you write out a lot of ugly algebra. That was literally looking at if my motion or my action is changing in either my X or my Y. So very, very real characteristic. In fact, the demo videos that you have for these chapters go into, I have this like cart going along and it shoots a ball up into the air and the ball lands back in the cart as the cart continues at constant velocity. And that happens because there is no force acting in the X direction, and we can do that in the classroom even. So for as much as you're going to hear here that we're ignoring air resistance for small actions, for things inside of the classroom, air resistance really has very little impact. So most of our demonstrations will hold true to this because you're not seeing an impact. There's no force acting in the X direction. And if we keep those actions minimal enough, then the air resistance isn't going to impact it that much. So as I throw this ball, roll this ball off this table, then its X velocity, well, there's no net force in the X direction. There's no air resistance. So as it's going towards the ground, its velocity in the X direction is constant. Let me write that down. Velocity in the X is constant without air resistance. Air resistance is air's version of friction. That's all it is. But you can think of it as small enough for small actions that our approximations are pretty darn good. Okay? So we can look at this then, we can say, okay, I'm starting off at some certain height, and we come back to this then. And I say, all right, when I look at these graphs, that parabolic motion that you see, well, that's just coming from my X vector is staying constant. They're not changing. They're all the same length. The only thing that's changing is that if I launch something off of a flat surface, so the ball example I have here, if I send it off this surface at that very, very split second that it leaves the table, it doesn't have velocity in the Y. All of its velocity is in the X. Okay? So I start off with no velocity in the Y. I get down here. Well, now the acceleration due to gravity, or gravity is my acceleration. Gravity is my force causing the acceleration. So I have this net force acting in the Y now. When it's here, it's not flying up in the air, falling down on the ground. It's just on the table. So my net forces in the Y are 0. I get over here. The only force I have acting on it, ignoring air resistance, reminding you we're ignoring air resistance, so the only force acting on it is the force of gravity. So I have a net force accelerating it down. So what's going to happen? Let's see. This is like re-emphasizing velocity vectors and those negative signs. If I have defined down as negative, I'm starting off at a 0 velocity. I get here and you see a small little chunk of a vector there. Well, I've had this amount of time for our force due to gravity to act on it. So I sped it up that much. Goes a little bit further. Now my velocity in the x is still carrying it that direction. The acceleration is sped it up by that much. It keeps going. Now my y velocity is increasing that much more. X velocity is constant. Keeps going. It's increased a little bit more. And it's going to happen. It's going to be this consistent increase as it goes down. Because the only thing acting on it, the only acceleration that it has, is acceleration due to gravity, and that's pointing straight down towards the center of the Earth. So if it's pointing straight down towards the center of the Earth, the acceleration due to gravity is constant. We're not doing anything to change that right now. We'll talk about how height changes that when you get to, it's more important when you get to heights like on top of mountains. But for here, it's constant. So there you go. So I have this parabolic motion. My acceleration is the acceleration due to gravity, and it's going downwards. Let's look at that in terms of a force, right? So if I take the ball, that split second after it's left the table, here it is. There is the force of gravity down. That is it. That's it. It's the only force acting. So if that's it, and I have no forces in the x, so the sum of my forces in the x, that's 0. There are no forces. Sum is 0. There's no forces acting, no acceleration in the x. The sum in my y, let's see, let's just call down positive for funsies. So sum in the y, what do we have here? I have just the force of gravity. So the force of gravity I've defined down as negative. So the force of gravity is going down, but so is my acceleration. So this is the only force I have. That means I have mass times acceleration. So I can rewrite the force of gravity because we've defined that as mass times gravity. And I can go, let's see, mass times gravity equals mass times acceleration. Oh, I feel like we've been here before. As I look at this, masses cancel out. This is how we get that acceleration equals acceleration due to gravity. That negative sign only comes in there if I have defined down as negative. What is true is that the acceleration due to gravity is always pointing in the same direction. It is not changing its direction. It's always pointing towards the center of the Earth. So in the next video, we're going to do some math with this.